So in this video I will start with how we can plot graphs actually, and this video is going to be very important for you, and from this video you will actually learn how you can plot graphs of any polynomial function or any trigonometric functions modified versions, not simple trigonometric graphs or simple polynomials, but and we will also see how we can transform a graph to by taking its mod, taking minus and negative and everything and all. Not in this video, but in today's video we will first learn about these three topics, which is concavity, convexity and points of inflection, and these three are the base, the roots of plotting a graph. And before we can plot a graph, we need to know about three these three elements, and this will help us in plotting any graph. Okay, so here I am taking a function, suppose y equals f of x, and we need to plot the graph of f of x, right? So what is, so I'm just telling you one thing, that whenever you are given any polynomial function or any trigonometric function, we need to check some characteristics of this graph, that is where it is increasing, where it has local maximum, where it has local minimum, where the value is maximum or minimum, and also at x equals 0 what is the value of y. So these are some characteristics of a graph which helps us in analyzing the graph and plotting the graph. So and how we can check increasing or decreasing, we differentiate both sides and take dy dx, and if dy dx is greater than 0, then we can say the function is an increasing function. We will also see about different intervals where a graph is increasing and a graph is decreasing, or a graph is decreasing, right? So if it's greater than 0, then the function is an increasing function, and now if dy dx is equal to 0, then it has either maximum or minimum, right? Actually, here if a polynomial is given or any function, first take dy dx equals 0 and see if it is actually 0 or not. Okay, if it is not 0, then you conclude that the function has no maximum, not maximum or minimum, just conclude that the function has no local minimum or local maximum. Because for an example, if a function is given like this, y equals x, then it has the maximum value is obviously infinity. As x tends to infinity, y also tends to infinity, right? But the dy dx of y equals x is 1, and 1 is not equal to 0, so this function has no local maximum or minimum. It has maximum and minimum, which is plus infinity and minus infinity. Okay, so and similarly, what will be the graph if dy dx is less than 0? Dy dx less than 0 is indicates that the function is decreasing in nature. So this was about all dy dx. Now we will see, now the nature of the graph is not only dependent upon dy dx, it also depends on d2y dx2, that is the second derivative. Okay, so we cannot actually conclude the nature of the graph from by taking only dy dx. We also need d2y dx2. By combining these two, then only we can conclude the curvature of a graph. Okay, now look carefully. Now we are taking we cannot take only d2y dx2 as a single element. Okay, so we are taking first dy dx greater than 0 and d2y dx2 greater than 0. Now this is the increasing function like this. Since both the values are is greater than 0, the graph looks like something this. It's increasing like this. Okay, the curvature is like this, means as x increases, y increases very rapidly. Okay, at a very fast rate, you can say. This is not a proper term to use, but you can use it for your better understanding. You can write like this, that this indicates if x increase, then y increases very rapidly, increases rapidly. This is for your understanding. Okay, now for the next part we have, since we are taking dy dx greater than 0, so the other case will be dy dx greater than 0, and here d2y dx2 will be less than 0. This will also indicate that the function is increasing but at a very slow rate. Why? See here, in the previous one the graph was like this, and here the graph will be increasing but will be like this, means x increase but y increases at a very slow rate, but y increase uh, increase at a very, we can give an example. Here we will see an example, very slow rate, and an example will be log of x. Here you can see that in graph of log x, we know that the graph of log x looks like something this. No, not this, sorry, right? So you can see that as x increases, y also increase but at a very slow rate. Why this happens? Take dy dx of, now here x is greater than 0, so x is always positive. Now dy dx of this will be, dy dx will be 1 by x. Now for x greater than 0, dy dx will always greater than 0 for all x. And what will be the value of d2y dx2? d2y dx2 will be, derivative of this will be minus 1 by x square. Now since x is positive and this is a positive number and that's a minus sign, so it will be negative for all x. So you can see that dy dx2 is greater than 0 and d2y dx2 is less than 0. So here the graph looks like this, that is x increase and y also increase but a very small, very slow rate. This is our, should be our interpretation for before plotting the graph. Okay, so this was the cases of dy dx greater than 0. Now we will see where dy dx is less than 0. Now this is our third interpretation, dy dx less than 0 and d2y dx2 greater than 0. Now what will be the nature of the curvature? See here, dy dx less than 0 means the function is decreasing, but d2y dx2 is greater than 0 means it is decreasing but a very slow rate. Just opposite, it will be like this. It means as y decrease, x, sorry, as x decrease, the y also decrease but at a very slow rate. Okay, sorry, I made a mistake here, actually not this one. The graph should look like this. Okay, actually these are very confusing part. Let me check just once. um, Here you can see that function is decreasing 1 by x minus 1 by x square, and it will be minus 2. Yes, right. So as you can see that here, let me write it properly. So this will be the curvature when dy dx less than 0 and d2y dx2 greater than 0. Okay, and the last interpretation of this will be dy dx less than 0 and d2y dx2 is also less than 0. This is strictly increasing, decreasing, and the curvature looks like this, right? So these are our four cases for determining the increasing and decreasing nature for our graph, and there are three more things to tell the maximum point, the minimum point, and where d2y and now you here I have written a case where dy dx is 0, and I have told you that this is the case where the graph is either maximum or minimum. Now what happens if d2y dx2 is 0? I haven't write it here yet, so now we will see what happens if d2y dx2 is 0. And so here d2y dx2 is 0 if this point is we called point of inflection, is point of inflection. Now this point, what does this point of inflection mean? This point of inflection is nothing but the point where the graph changes its curvature. That means, suppose you have a graph like this and it's just wait, and it's increasing like this. Okay, now at this point, suppose this is our point of inflection and it changes its curvature. Just wait, and it changes its curvature and it starts increasing like this. Now, and this point is dy dx greater than 0 and d2y dx2 less than 0, right? And and this part is where dy dx is greater than 0 and d2y dx2 is also greater than 0, and this point will be point of inflection where d2y dx2 will be equals to 0. Got it? So it is the point where the graph changes its curvature. Okay, so I hope this is clear to you. Now we will see what will be our maximum value and what will be our minimum value. So as I have told you that maximum and minimum values is the point where dy dx is 0. Okay, suppose if dy dx is a quadratic of second degree, and then you will get suppose two roots x1 comma x2. Suppose these are the two roots of this equation. Okay, now what will be the minimum and what will be the maximum? There is a way to tell that, and here also d2y dx2 helps us. So put d2y put x1 first, put x1 in d2y dx2, and see if it's greater than 0, then we get minimum value. Okay, either minimum or local minimum. So let me clear the confusion first. If you see any graph is tends to minus infinity as x approaches minus infinity, then the minimum value is minus infinity. And if you and then if you see that in that graph at some point the dy dx is 0 and d2y dx2 is greater than 0 at that point, then it will be the local minimum. Okay, now the second case is if d2y dx2 is less than 0, then it will be our maximum value. Now, okay, so these are our key points. It might not be clear to you right now, and it will take some time to grab it properly and have a proper understanding over it. So I'm just showing you a diagram from where things will get clear to you. Okay, just look carefully. This will clear many confusion. See, suppose you are here a graph is given like this. I'm not drawing the axis, otherwise it will be messy. So here the graph, right? Okay, so you can see these are the points where dy dx is equal to 0 and it approaches minus infinity to plus infinity. Just wait. um, so here you can see that, just give me a second, it approaches from minus infinity to plus infinity, and these 3 points where dy dx is 0. Now I am starting from the leftmost point, which is this point. You can see that this point is, now look carefully, there are 4 points, sorry. So you can see that this point is above, I mean, it forms a trough. If I am correct, the in a wave, if the upper part is called trough and the lower part is called crust, if I am not wrong. Maybe I am wrong, just check it once. So I'm just using the term upper part and lower part. If it forms a bound in the upper part, then you can, if you see the graph, you can take it as a local maximum. And here, if it is local maximum, then you will see that this point dy dx is equal to 0. uh, just wait. So here at this point dy dx you will get 0, and d2y dx2 you will get less than 0. So this is our first local minimum. And why local minimum? You can clearly see that uh, the graph is no, the maximum value of the graph is function is infinity, so we are using the term local maximum, sorry. And this point will, you can see that this is local minimum, and here also dy dx will be equal to 0, and d2y dx2 will be greater than 0. Okay, similarly now you can conclude this point and this point also. Here also you will get dy dx equal to 0 and d2y dx2 less than 0. And again this will be same as this one, so I'm not writing it again. And if you see here, look carefully, you can see that here the graph changes its curvature again. See here, actually this should be like this, so more smooth for better understanding. So consider the red part. So here you can see this point, in the left hand side, this point the graph increases but at a slow rate, that is dy dx greater than 0 and d2 dy dx2 less than 0, and here both value is 0, I mean greater than 0. So this will be our point of inflection, point of inflection, right? And point of inflection means d2y dx2 equal to 0. So I hope this is clear to you, and see this diagram for better understanding. And I am just writing it properly. If you want, you can write my what I'm saying, if you haven't make any notes yet or not, but I'm writing it once again. If the maximum value of a function is okay, don't worry, I will upload the note in the Telegram. You don't need to sit and write and the whole thing. So I will upload it later, and just watch the video for now. And if you have any doubt, you can join the Telegram group and ask there. And so here's I'm just going through the full notes once again. So first we see the nature of the graph based on dy dx, and then we included d2 by dx2. We see the different forms of curvature based on by combining dy dx and d2 by dx2. That we see points of inflection, then maximum and minimum values, local maximum and local minimum. Then from this diagram we see all these things in a single diagram, so it's better for you. And I am okay. In the next video we will plot some graphs and see some examples of polynomials only, because it will take some time to properly understand the graphs, properly analyze the graphs, properly see the curvature. And okay, it will take some, at least you need to practice at least 5 to 6 graphs of polynomials to properly learn them and properly analyze any graph of polynomial. Then after that I will go to transformation, then logarithm graphs, exponential graphs, and other trigonometric transformations and everything. So next video I will complete some I will discuss about 3 to 4 graphs examples of polynomials, and we will plot them in the next video. Okay.